Welcome to Ask Melissa Maribel Live, where you tweet your questions ahead of time for a chance for me to answer them on my live show. Thank you so much for being here. I see that this live chat is goodness, this is a party right now. I see so many people here. I want to say hi to as many people as I see. I see Donna, I see Andre, Ryan, Abraham, a lot of different people that I haven't actually seen you guys before, I feel. So welcome if you're new to this live show. What happens here is you tweet your questions ahead of time, and then I prepare a lesson, a nice detailed lesson just for you and for actually multiple people's questions. So that's kind of what I'm doing now in this sort of style. I'm excited to share what I have in store for you guys. So I have titrations and I have rates of reaction. This is going to be a great lesson. This is literally $100 worth of tutoring that you guys are getting completely for free. So I'm super excited to kind of share this with you guys and explain titrations because I know how tricky it can be since there are so many steps. Now, for the people who did tweet me a little bit later, I do recommend actually tweeting me before Saturday. So like Friday night at the latest, because on Saturday morning, I actually decide what I'm going to teach on and I actually, pick my lesson. So for everyone who tweeted me today, I'm not going to be able to answer your questions just because I really, picked out my entire lesson plan and I have all of that done. Okay, so make sure to tweet me ahead of time. So Friday at the latest, or even like throughout the entire week, I highly recommend doing that just so I can see your question. Okay, so this is what we're going to talk about, titrations and rates of reaction. Now, by the way, if you guys do have other questions, and let's say, I can't answer them here, I do have more resources in the description box, so make sure to check it out. It's all the way at the bottom. I have more resources at the bottom with like online tutoring if you need a tutor. I also have, homework help, which I personally recommend. It's called Chegg Study. I used that all throughout college, and it was a lifesaver because a lot of times, I don't know about you, but I remember my homework being difficult, and a lot of times I'd see some of the questions like, what in the world is this question even asking me? So Chegg Study was a lifesaver with that because it was even more affordable than having a tutor, and I got that the entire month. So I highly recommend checking that out. It's in the description box at the bottom. And then just a little disclaimer, I am part of their affiliate program. So if you do decide to go with Chegg Study and purchase it, I do get a small commission that just goes to making more videos for my channel. All right, so let's begin. We're going to start off with titrations. And by the way, if you're watching the replay here, I will be putting a pinned comment at the end with all of the timestamps so you know exactly like when I started talking about equivalence point or rate of reactions and so on. Okay, so let's dive in because I see some people have tests coming up. Someone has a titration test tomorrow. So yes, let's dive in and get you a better grade. All right, guys. So titrations. This is going to be really important to know what in the world titrations even are. Okay, so a lot of times you're going to see this in lab. That's where you're probably actually going to see this first because I don't know, it never matches up with lecture and lab. But what's happening in lab is titration is essentially talking about an acid-base neutralization reaction. And all that's really talking about is you're going to see some sort of setup like this, okay, where you would have some sort of acid. And actually, I believe I labeled this. Cool. So you would have something in like a flask, okay, and you would have a certain amount of concentration of acid. And what you're doing is it's called you're titrating base, just meaning you're dropping base into the acid, okay? So as we're, dropping the base into the acid, what's happening is we're trying to neutralize this overall reaction, okay? So that's the whole point of titration. The point of titration is to get to neutralization, and where we get to neutralization is actually called the equivalence point. So what's going to be happening in lab, this is like a good demonstration of what's going to be happening in lab, is we're slowly going to be adding our base. And what's going to happen is this acid is actually going to start changing colors. The reason why it's going to change colors is because initially in the acid mixture, what we would have done is we would have added something called an indicator. Specifically, I believe you guys use phenolphthalein. All that is an indicator makes the acid turn a specific color so we know that we've reached neutralization. Okay, so what's going to happen, a lot of times you're going to see the acid turning pink, and it looks really cool. But what you want ideally is to have your acid turn into this really light, faint pink. And that's how you know you did this right. So once that you have that color that's really light, faint pink for your titration, then that means you reach the equivalence point or you reach neutralization. So in this case, what that's talking about is we have the same amount of concentration of our acid as our base. That's equivalence point. You have equal amounts. So, and I don't want to say the overall volume is equal. It's the concentrations that are equal, okay? So that's something to note when we're talking about these sort of titrations. Now, what you will also see, like this is the goal, by the way, in lab. You want to get to that really faint pink, and you know that you did it right. Oh, by the way, little tip with lab. So when I started doing this in lab, I would always get my titrations like perfect, and I wouldn't have to do it again over, a lot of times you have to do this over again, and this process takes so long. So my little trick for you in lab is put like a white piece of paper underneath, and I'm going to just pretend that this is a white piece of paper. You'd put like a white piece of paper, and then on top you would have your beaker, and then as you start to just drop the base, I always laugh at that, sorry. So as you drop the base and mix it around a little bit, then you're going to see like a light faint pink, and that white piece of paper, that reflection is going to help you see, oh, okay, it's actually a light faint pink, or else you're just going to see like the reflection of whatever countertop you have. So it makes it a lot easier to see when the actual equivalence point is happening. So I highly recommend using that. Like I said, whenever I would use that trick, I would be like, my titrations would go so well. So let's keep going with that. So let's say if you added too much base, right? Then what would happen is you'd have this really bright, darkish pink. And that means you added too much base. So it's past the equivalence point now. So instead, now it's after the equivalence point. And essentially what we have is our concentration of our base is now greater than the concentration of our acid. So, and really, actually, I would even say that it's just our base right now. So all we would have is the concentration of our base because we added so much of it. So understanding kind of how this is going is going to be really beneficial when we're actually doing the math and, being asked these specific questions. So I hope that's kind of, coming together and making sense why we're doing this process. So I just want you to think titration, we just care about like neutralizing everything, making the concentration of our acid be the same as the concentration of our base. Okay, let's do one. So another thing that we're going to talk about is strong acids, strong bases, weak bases, and so on. And actually what you'll see on the screen right now is I do have notes talking about acids and bases, and that's like the beginning portion. So if you need to review your acids and bases, like let's say how you actually get the formulas, what your conjugate base pairs are, or how to find the pH, pOH, and so on, I highly recommend checking that out. It is currently on sale, and that I can put the link for that acids and bases. Actually, I believe the link is in the description box, but I can also put it in the chat. Highly recommend checking it out. I have a really detailed guide on everything acids and bases that you will need before we get into titrations, which is going to be kind of like the foundation of it. So I highly recommend checking that out. Okay. So, and by the way, also another thing, in the description box, I have this strong acids and weak acids list. It's my free survival guide, the chemistry survival guide. You can download that in the description box. So that's going to be there as well. So any of these lists or any formulas that I'm talking about, that's also in that guide. Okay. So make sure to download that if you haven't already. Okay. So there are things called strong acids and weak acids. Our strong acids will completely dissociate. All that means is dissociation means it's going to break apart into its ions. So here's an example. So like let's say HCl. HCl is a strong acid. And then dissociation is really just talking about that this is going to break apart into its single ions. So like H would be on its own, and we know that hydrogen has a +1 charge. And then Cl, or chlorine, has a -1 charge, and that would break apart as well. So that's what we're talking about with strong acids. And actually, look at all of these. These are all completely dissociating, right? They're all breaking apart into their ions. However, for a weak acid, it's not going to completely break apart. And a good example of this is, let's say, sulfurous acid. This is H2SO3. It doesn't completely break apart, right? Sure, H is by itself, but we still have HSO3. So that's kind of the concept with strong versus weak. Yes, you do need to memorize this, okay? So make sure to know your strong acids and your weak acids because that will come up. All right, so I'm going to keep going to our bases, so our strong bases and our weak bases. And I have a little trick for you to remember your strong bases. So for your strong bases, looking at all the metals that are in front, like lithium, sodium, we have potassium, and so on. So all of these are going to be in the first two groups of our periodic table, right? So if we're looking at lithium or sodium and let's say even calcium. Yeah, calcium should be here. So calcium and so on. So if they're in the first two groups and they're attached actually to OH, that's most likely going to be a strong base. Okay, so the first two groups of your periodic table, those metals, and if it's attached to OH, then we know it's a strong base. For weak bases, it's different. The main weak base that you will see is ammonia, so definitely know that one for sure. These are other ones that I've seen, but really, the main one that I would say to just know is NH3. Okay, so I always see that one. But these are all ones that, yes, you do need to have memorized. Okay, so beware of that. Okay, why is this important? Because you're not going to be told whether something is a strong acid or strong base. And you have to figure out what type of titration is this, okay? So there are two different types that I'm going to go over today. And the first type is going to be the strong acid and strong base titration. The second one will then be a weak acid and a strong base titration. So there's multiple steps to these two different types, okay? So beware of that. So the first one that I'm going to talk about is a strong acid and a strong base and what's essentially happening. So how I instantly knew that this was a strong base and strong acid was just based on the list that we talked about previously. So HCl, we said that's a strong acid. NaOH is a strong base. So, okay, that's how I know strong acid, strong base, that's the titration that I'm focused on. So let's see what this is asking us. It's saying determine the pH at different volumes. So every single one of these volumes, and by the way, the volumes of all of these, this is going to be of NaOH, right? So we're talking about our base for every single one of these. And then in a titration of 35 mils of 0.4 molar solution of HCl, that's our strong acid, and then they give us our molarity of our strong base. Okay, before I do anything, what I highly recommend you guys do, and always do this, is to figure out what your equivalence point is. And I'm going to go back to that demonstration that we had. Let me see if I can, with the titrations, because this is going to help. Okay. So essentially, and I can't erase that, darn. Essentially what I'm talking about here is your equivalence point is when our acid and our base are the same concentrations, right? That's what we talked about before. Now, when we're actually looking for our equivalence point or really just the volume of our base, so I want you to think of it as what we're essentially doing right now is we're figuring out how many milliliters, and we said our base is NaOH, how many milliliters of NaOH do I need to drop in order to get that equivalence point? So that's what we're solving for. We're solving for how many milliliters of NaOH do we need to neutralize this acid. That's what we're looking at when I'm talking about equivalence point. So that's exactly what we're going to do. All right, let me speed this process up. There we go. Okay, so this is going to be stoichiometry again. What we're going to do is we're going to go from the milliliters of our acid, so HCl, and then we're going to make our way, and there's going to be several different, things that we have to go along with this, and we're going to make our way to milliliters of our base because that's what we're trying to get to. We're trying to see where is our equivalence point. So here's our plan. And before I get to that, this is going to be our overall plan, okay? This long list, because we're going from our milliliters to our milliliters of our base. All right, and let me see if I can erase some of this. Another thing that you will also need to know is how to actually write the balanced equation. They will not give you a balanced equation. So the fact that we knew that HCl was a strong acid and this was a strong base, and we talked about that this is really titrations are just acid-base neutralization reactions. Well, what is an acid-base neutralization reaction? Well, that's an acid plus a base, and its product is a salt and water. So this is exactly how I knew how to write this formula, because our acid is the one that starts with an H, right? Our base is the one that ends in OH, And weak bases are obviously different. That's NH3 and so on. But at least looking at this one. And then salt will be formed. And how we can see this is Na and Cl combine to form our salt. And then HOH really just means water, right? So that's essentially what's happening. Everything's balanced and we have our balanced equation. Make sure to do that as well. So the first things that I want you to look at, write your balanced equation, right? Write your balanced equation. Next, write what you're going to do for your equivalence point. So we're going to find our equivalence point essentially. So those are the two main things that you're going to do before you actually dive into finding the pH of anything. All right, so let's figure out what our equivalence point is going to be. Let me explain how I knew exactly how to do this, okay? So I'm always going to start off with what I'm given. And I'm given milliliters of HCl, right? 35 mils of HCl. So that's what I would start with. And yes, you will start with the volume of your acid or whatever was in that beaker, right? And then it's called a titrant, meaning that base that was in that burette. So essentially that's what's going to be happening here. So I'm going to start off with the milliliters of our acid. And then next, I'm going to change that to liters using 1,000 mils is equal to 1 liter. And then next, I'm going to use the molarity that was provided. And our molarity that was given was this 0.40 moles over liters, because remember, capital M just means moles divided by liters, all right? So that's kind of the main thing that I want you to look at, by the way. With molarity, we're pretty much piecing everything that we previously learned in Gen Chem 1 or the first half of chemistry, and we're now putting all of these ideas together. So just knowing that molarity is moles divided by liters, that's going to help us because that helps us get to moles of HCl. Next, we want to do a mole-to-mole ratio to change the compound. So we want to get to moles of NaOH, and we use the balanced equation for that, right? Just the 1-to-1 relationship that we see here. And then from there, we're going to continue and try to change this to liters. And how we're going to change this to liters is because we have the concentration. So our concentration or molarity allows us to go from moles to liters or vice versa, liters to moles. So that's what I would use right here. I would use the molarity of NaOH. Lastly, since we have liters of NaOH, we're just going to convert this back down to milliliters using 1,000 milliliters is equal to 1 liter. Okay, so let's do that. Let's set everything up. So setting everything up, I'm just starting with what we were initially given. So 35 mils of HCl. Next, we said we wanted to change this from milliliters to liters. So I have to align my units across so they can cancel. So 1,000 milliliters per every 1 liter. And so far we see that milliliters and milliliters will cancel. And we'll keep going. So where are we at now? We're at liters, right? We're right here. We're at liters of HCl. So next I have to get to moles of HCl using the concentration that was provided initially. So the concentration that was provided initially, I'll write it up here, was that 0.40 molarity of HCl. And we said molarity can be broken down into moles per liter. And we'll note here that that number, whatever number is in front, is actually going to go with the moles. So that's why I placed the moles on top, okay? And then liters will go on the bottom, and that will be 1 liter on the bottom. And then we wanted that on the bottom because we want these to cross out, right? They want them to cancel, which they do. So liters and liters cancel. Now we're at moles of HCl. All right, next thing. So since we're at moles of HCl, now we're going to get to moles of NaOH using the mole-to-mole ratio, which was found in our balanced equation. Okay, so that was just a 1-to-1 relationship because everything was balanced. And then from here we see, okay, our moles of HCl, those are cancel. And then now we're at moles of NaOH. Once again, we're going to use another molarity that was provided. So the other molarity that was given to us, and I'll write that here. The other molarity that was given to us was 0.20 molarity of NaOH. I can rewrite this as 0.20 moles of NaOH divided by 1 liter. Now you'll note that these are flipped, and we're allowed to do this because we want the moles to be on the bottom so they can cancel, right? We always want our units to be across from each other so they can completely cancel. So here our moles and moles cancel, and now we're at 1 liter. Then lastly, we'll change this to milliliters. So we know that 1 liter, for every 1 liter, there's 1,000 milliliters. And then from here, this would then all cancel. And then we'll multiply straight across. So really multiply straight across. Then divide by everything else on the bottom multiplied. And we would get 70 milliliters of NaOH. So that's our equivalence point. So why is that helpful? That's going to be helpful because let's go back to the question and then we'll be able to see what our equivalence point is, and I'll explain a little bit further what everything means. All right, so we know that our equivalence point is 70 mils, right? So that means I know that part B, the 50 milliliters, is before equivalence point even hits, right? So I know, okay, that's before equivalence point. Our 70 mils is our equivalence point. And then anything after that is after our equivalence point. And essentially what that's talking about is if our equivalence point is telling us that the concentration of acid is the exact same as our concentration of base, that means that it's neutral, right? So that's where it neutralizes because it's a strong acid, strong base combination here, titration. So that means that if it's neutral, then our pH must be 7. And I really answered part C. So, and that specifically, by the way, is just for a strong acid, strong base. It is not the same for a weak acid, strong base titration. Okay, so that's why I'm showing you 2 different types. And these are common test questions. So now, if I'm looking at part B, before equivalence point, well, if it's before equivalence point, that means I haven't added enough base, so it's most likely going to be more acidic. Right? So this is why knowing the equivalence point is going to help us so much because we'll be able to figure out, is it going to be more acidic? Is it going to be more basic? Is it going to be neutral? So now at part D, where it's after the equivalence point, that means we added too much base now. So that's that bright pink that we talked about before. So it's too much base, meaning it's going to be more basic. And by all of this, I'm really talking about the pH, right? I'm talking about the pH. So if it's going to be acidic, that means it's going to be less than 7. If it's going to be basic, our pH will be greater than 7. All right, so now let's get into it. Let's actually do the math. All right, so here, let's talk about, let me go back actually. Sorry about that. All right, there we go. Okay, so let's start off with part A. Part A is telling us we haven't added any base whatsoever, right? It tells us there's 0. So there's 0 milliliters overall of NaOH that we've added. So essentially, we just have acid. That's all it's telling us. We haven't added any base whatsoever. So that makes us very acidic. And especially if this is a strong acid, then I know that my concentration of my acid, which is this is H+. By the way, you might have also seen this as it's called hydronium ion. That means the exact same thing. It really is just talking about our acid concentration. So if we haven't added any base at all, then I know that the concentration of my HCl, of the strong acid that was provided, is the concentration of my hydronium or my acid concentration. And how that's helpful is I can just instantly plug that into my pH formula. All right, so I can plug that into my pH formula, and that's exactly what I'm going to do. So this is our pH formula. And by the way, all the formulas that I'm talking about are in the description box in my chemistry survival guide. Make sure to download that. All the tables, list, everything that I'm mentioning here, that's all there. So make sure to check that out. And by the way, also, there's also more resources. So if you guys are kind of coming into this later, like if you're just joining right now, or if you have other questions, like you need homework help or online tutoring or anything like that, make sure to check the bottom of the description box. I do have more resources there, specifically Chegg Study. I personally really liked that when I was in college, and I still love it today. I think it's really beneficial. So if you need more help with, let's say, your homework, you want to see how in the world to even, understand your homework and you want an explanation, I highly recommend checking it out. It's even more affordable than a tutoring session, and I completely remember what it's like to be a college student and not be able to afford tutoring. So definitely want to give you guys more resources that are affordable. So make sure to check that out. And little disclaimer as well. I am part of their, affiliate program. So if you do decide to go with Chegg Study, I do get a small commission, which just goes to making more videos for my channel. All right. So just wanted to mention that. All right, so let's go back to this. If we haven't added any base and we just have our strong acid, plug it in and we're done. So I'll plug it in, I'll plug in our concentration of our acid, and then let's actually do this together. I'll do negative log and 0.40, and this is going to tell us what our pH is. And remember, our pH must be very acidic because it's just a strong acid. The only thing that's there is an acid. So I know that, okay, actually, it's the same exact thing basically. So our pH is 0.40, making it really, really acidic because anything that's less than 7 is going to be acidic. So that makes sense. Now I'm going to keep going to the next part. So part B. Okay, so for part B, we're just going to look at 50 mils. So this means we added 50 milliliters of NaOH. And this is before equivalence point. Now remember, before equivalence point still means we haven't added enough base and it's going to be acidic. So this has to be acidic. So then that's why the formula that you will use, and by the way, with this, you don't have to use an ICE table. You don't have to use a before change and after table, a BCA table. So I kind of prefer not to. Sure, you can, but it makes it more complicated, I personally feel. I will go over that though. I will go over that for the second type of titration that I'll talk about. But for now, this is going to be, I'd say, the simplest way. That's why I like to teach it this method. But if it's before the equivalence point, you're still looking for your acid concentration, right? So since I'm looking for my acid concentration, essentially what I'm going to do is I have to find the moles of our acid, subtract that from the moles of our base, and then find the total volume. So meaning, and we'll get to actually doing everything, we'll divide that by our total volume because this has to be molarity. It has to be concentration. So what I'm going to do first is just this first part. I'm going to figure out what the moles of our acid is. So we'll find the moles of HCl, starting with 35 milliliters of HCl that we were given. So that's what I'm going to do. Next, I'm going to change this to liters. So our milliliters of HCl would cancel, and now we're at liters. And then next, I'm going to use the concentration that was provided. So here we have molarity, and that's going to be broken apart into moles divided by liters. So that can cancel again. And then now we get our moles of HCl, which would be this answer. Okay, so that would be the moles of HCl. Now I'm going to keep going, and I'm going to see the moles of our base. So we want the moles of NaOH. And what I'm going to do is I'm going to use what they gave me. So we said in part B, they're giving us 50 milliliters of our base. So that's what I'll place here. I'm going to convert this to liters using the same approach. So milliliters cancel. We're now at liters. And then next I can use the molarity that was provided again and change this to moles over liters to give us our moles. So we have our moles of our base. All right, so far so good. And then next, with our total volume, where I'm taking this from is we initially were given 35 milliliters of acid, right? And I have that here. Then next, we're also given in part B 50 milliliters. And yes, this will change each time depending on the part that you're on. So for part C, it will change, just letting you know. So 50 milliliters. So, okay, we have 50 milliliters. We'll add those two together, which gives us 85. However, we want this to be in liters. So since this has to be in liters, our milliliters and milliliters will cancel. And now we have it in liters, and okay, we have everything so far. So we have our volume, we have our acid and our base. Now I'm going to plug everything in and subtract. So when we do that, after we plug everything in, we subtract those two and divide. This gives us our concentration of our acid, which is this. And all I have to do is plug it back into that formula, right? I have to plug it back into our pH formula, which is the negative log of our acid concentration. So when I do that, I get, oh, you know what, let me go back. That's right. I was going to do this with you guys. So let's see what we get. Negative log 0.047. All right. This is going to give us a pH of 1.33. And then this makes sense because it's before equivalence point, meaning it's acidic. Right? So since we know it's going to be acidic, yep, that makes sense. Our pH is less than 7, so it has to be acidic. So that works. And then the next step, the next one is actually at equivalence point. And remember we stated that at equivalence point, our pH will be neutral, just meaning that it's going to be neutralized, right? So we were talking about there where the concentration of our acid is the exact same thing as our concentration of our base. And when that happens, our pH is neutral and our pH is then 7. And that's really all you have to do. So that's why it's so important to know what your equivalence point is, because it makes the steps a lot easier to figure out, oh, is this before? Is this after? Is this actually at equivalence point? So, and once again, this is only for a strong acid, strong base titration. And the last part is talking about when it's after equivalence point. So we stated that after equivalence point, that means we added a lot of base. So this is going to be basic. And that's exactly why the formula changed, because now we're looking at just the concentration of our base because that's what's left inside the flask or the beaker. So in this case, we're going to have more moles of base than of acid because that gets all used up. So we neutralized it. Now we're adding a lot more base. And then we're going to divide it by the new total volume since we added more NaOH, right? Now we're adding 80 milliliters of NaOH. Okay. Our moles of acids, that's actually going to stay the exact same. So I left that here. Nothing changed, right? We didn't change the amount of volume that we added of HCl. We didn't change the concentration. So that's the exact same. What did change is the moles of NaOH. So now we have 80 milliliters of NaOH. We're going to convert that to liters. And this is going to cancel. So milliliters cancel. Now we're on liters. And then we'll use the concentration that we did before. So that molarity, I'm going to split that apart into moles divided by liters. Liters and liters cancel. We're now at moles, and this is what we would get. Okay, this is what we get. So now for our new volume, what we're going to do is we're going to add the 35 milliliters of our HCl and add it to the new volume of base that we just had, right? Because we changed that. So we have 80 milliliters plus the 35. So that gives us 115. We're going to divide that by 1,000 to convert it to liters. And then now we have everything. So we'll plug everything into the formula. When we do that, we get this new concentration. Now note, this is the concentration of base. It's not the concentration of acid. So we have to figure out what our concentration of base is. And there's a specific formula for that. So this is our formula that we will use to figure out what our concentration of acid is. Then we can plug that into the pH formula and figure out what the pH is. Okay. So what I'm going to do is I'm just going to plug this in. So I plugged it in for our base. And then next, all I have to do is divide both sides by this value to figure out what our acid concentration is. So I'll do that. And then let's figure out together what our concentration of our acid is. So I'm going to divide that 10 to the 14th, negative 14th, divided by 0.017. And that would give us 5.88 times 10 to the negative 13th. And then next, since we have our acid concentration, what I'm going to do now is I'm going to plug it into the formula of pH is equal to negative log of our acid concentration. So I'm going to plug that in here. And then we'll see what that pH would have given us. So when I do that in my calculator, that's going to give us roughly 12.23. And that makes complete sense because it's after our equivalence point, meaning it's going to be more basic. And any pH value that is greater than 7 is basic. So check. Yep, that's right. So this is essentially the whole process that you would go through to figure out a question like this for strong acid, strong base titration. Let's do another one where it's a little bit different now. This is going to be a weak acid and a strong base. And I'm going to tell you how I can just instantly tell that this is a weak acid. So let's read this first, and then I'll tell you my hint how I know it's a weak acid. So calculate the pH at different volumes in a titration of 40 milliliters of this concentration of formic acid. And it gives us a Ka value with our 0.1 molar solution of KOH. Okay, so how I know this is a weak acid? The fact that it has a Ka. So if it has a Ka, most likely is going to be a weak acid because our strong acids don't have Kas. All right, so that's something, if in the case you forget the list, then that is my trick for you. That if you see that there's a Ka, especially if there's anything to the negative 4th or negative 5th and so on, then you know, yes, it is a very weak acid. So that's how I instantly knew, without even having to memorize the weak acids list, that this was a weak acid. You do, however, have to know that KOH is a strong base. Will you ever see weak acid, weak base? No. Okay, so not much would really go on there, but you're not going to be given a question like that. Not that I have ever seen. So yeah, just beware of that. Okay, so there's new things that we have to do here. Now, the first thing, of course, we're going to have to find the equivalence point, because that's always going to help us know, what do I have to do? What are the steps that I have to take? So with a weak acid and strong base question, you will have to use something known as an ICE table, as well as a before, change, and after table, BCA table. I'll explain what all this means, but this question does take longer, okay? So beware of that. Okay, so let's find our equivalence point, and actually let's find our formula, balanced equation. And all I did was I combined our formic acid, which is here, and then our strong base, so KOH, and the same thing's happening. So essentially what's going to happen is CO2H and potassium are going to combine. Potassium is going to be first because that's the metal, right? We want our metal, then our nonmetals. So that's where we get this first salt. And then next we would have water. So H and OH would then form water. So far that's what we have. Okay. So then the next thing is to find our equivalence point. Now, the same sort of process actually occurs here, where we're going to start off with the milliliters that was given to us for our formic acid. And then next, milliliters of our base will be what we're trying to get to, right? So for our equivalence point, remember, whatever you're trying to find, and what I mean by that, whatever these values give us, and they're giving us how much KOH is actually placed in the solution, or how much is actually being titrated or dropped, right? So that's essentially what we're looking for. So we're going to do this whole process again. And, all right. So I set it up already for you guys. I'll explain where I got all these numbers and how to do all this. This is, once again, doing the same sort of process we did before to figure out what our equivalence point is. So we were given 40 milliliters of our formic acid, right? And then across from each other, we place our milliliters. So that's going to cancel. Next, we're at liters of formic acid. And then now I have to use the molarity that was given. So our molarity of formic acid was that 0.1 moles of formic acid per every 1 liter. So that's going to cancel. Now when we were looking back at our balanced equation, everything was 1-to-1 again. Everything was balanced. So here I can just see that that's a 1-to-1 relationship. That's where I got it, that multimole ratio, right? This is going back to stoichiometry. So this cancels and this cancels because they're the same unit, and we'll keep going. And then now I'm using the concentration of KOH that was provided, placing the moles in the bottom so they can cancel per every 1 liter. And then lastly, I'm just converting this to milliliters. When we do that, when we multiply straight across and divide by these values on the bottom, multiplied, then we get 40 milliliters of KOH. That is our equivalence point. Okay, so our equivalence point is when we titrate 40 milliliters of KOH. That's when we actually get equivalence point, or meaning the reaction is neutral. Okay, so that's what we're going to look at. Let's go back to the question. So we're going to have something known as, and actually, let me just put them all up. There we go. Okay. Understanding what's before the equivalence point, what is the equivalence point, what's after it, and so on is going to be really helpful, because there are a lot of tricks to some of these questions. So, and what I mean by that, there's shortcuts, okay, that you can use, which I'll teach you. So when we're looking at this, we said that our equivalence point was 40, right? That means that's where it's going to be neutral, but it doesn't mean that our pH will be 7, unfortunately. Okay, so it's actually going to mean our pH is a little bit above 7. And the reason I know that is because this was a weak acid, right? This is a strong base. Which one wins? The strong base. So that means at equivalence point, our pH is going to be more basic because of this strong base, because it's stronger. So that's essentially the concept there. If we had it the opposite way, where this was a strong acid and this was a weak base, then our equivalence point pH would be a little bit more acidic, because that strong acid wins versus that weak base. Okay, so that's essentially the concept here. Now, the other thing that I'll talk about is something known as the half equivalence point. And all that means, it kind of sounds exactly what it sounds like, really. Equivalence point, 40 milliliters, it's half of it is literally taking half of it, so dividing it by 2. So this would be 20 milliliters. Okay, so that's our half equivalence point. So what that's telling us, there's a little shortcut here, where pKa is equal to pH. So that's our half equivalence point. pKa is equal to pH. I'll explain that a little bit further, but this is going to be a lot easier because we won't have to build an ICE table or a BCA table or any other table. We'll be able to just plug this into a formula and we're done. So that's why it's really nice to identify that. And then 39 mils of KOH is going to be before our equivalence point. So we know that if this is going to be pH is a little bit greater than 7, it's going to be a little bit more basic. Then I know that this is most likely going to be a tiny bit, it's an ugly A. Okay, a little bit more acidic. Okay, and then after that, after the equivalence point, that means we keep adding more base, then I know this is going to be very basic. So our pH is going to be even greater than 7, and this one's going to be less than 7. Okay, so what I'm going to do, let's dive right in because I don't want to run out of time. All right, so what I'm instantly going to do is not worry about KOH. All right, so what's happening here, and this is called an ICE table, is I just care about my weak acid right now. And the reason why I care about that is because I have to figure out what X is, or I have to figure out, and what I mean by this, X is going to represent our acid concentration. And if I figure out what my acid concentration is, which in this case is X, right, is then I know I can just plug that into the pH formula and then figure out the pH. So the reason why I can just automatically do this is because we haven't added any base whatsoever, right? That's why I don't have base at all in this question. So, and really just water, but it's pretty much just dissociating. Now, there's no base added. That's why I'm just looking at an ICE table, and that's all I can do here. So this is even before adding any sort of base, all right? So let's make a note of that. So in this case, I know initially, so the I means initial concentration, and this has to be in molarity, by the way. So I know that that's 0.1 because that's what we were given. Water, we don't worry about water. We don't care about it, all right? So it's in its liquid state. We don't worry about that in Ka. We only put aqueous solutions or gas, but don't worry about gases. We're not going to see that here either. So now what we would also place is we don't know what our acid concentration is initially because we haven't produced it yet, right? We just know our reactants, and then we don't know what our conjugate base is either. That's just going to be 0. The next thing for an ICE table is called the change. So our change is going to be minus X. So it's always going to be minus on the reactant side since we're using that up. And it's always going to be positive on our product side since we're making that or producing that. So in this case, this would be a minus X. This would be plus X and plus X. One little note, if this were a 2 in front, then this would have been a 2 in front. Okay, so it does depend on whatever coefficient we have. But in this case, we don't have that. So just wanted to make a note of it, though. Okay, now we're going to keep going, and the E stands for equilibrium. So when this is at equilibrium, what that means is the chemical equation is balanced, or the chemical reaction is balanced. That's essentially what we talk about with equilibrium. Now, what I would do is I would combine these all. So I'm adding both of these together, okay? And that's exactly where I then get the E, or what it's equal to, the equilibrium. So in this case, I know, okay, that's going to give us that, this gives us X, and so on. And the next thing that I'm going to do is build my Ka. So like I said, I know Titrations puts everything that you previously learned in one, kind of. So make sure to kind of go back if you're not too sure about stoichiometry, double check that I have a playlist on it. If you're not too sure about molarity and so on, practice that, okay, because that will be really beneficial for titrations. Now, forming that Ka, remember that Ka is going to be our products raised to some sort of exponent divided by our reactants, concentration, raised to some sort of exponent. Okay, but the exponent, how I know, since all of these are ones, we don't have to worry about that being raised to a specific exponent. But in this case, what I'm going to do, let me see if I can put this enough room, give myself enough room. Here we go. is I would have these products here. And what did we say those products are? Well, it's x and x. That's where I get x times x, which gives us x squared. And then next, my reactants have to go on the bottom. I don't care about the water, so that's where this is going to go on the bottom. And that's how I'm building this Ka, okay, so this expression. So then the next thing that we're going to keep going into is the idea of x is small. So in this case, x is small. I don't have time to test the theory, but I do have, goodness, a video talking about, actually, a previous live that I did recently, I talked about x is small in that theory, as well as how to make Ka and Kb. Yeah, I did talk about that. So make sure to check that out as well. I can see if I can put that in the link after, in the link in the chat after. But for now, I'm just going to assume that x is small. And when I do that, that removes this x value. Okay, so that completely bypasses that. So what I'm going to do now, goodness, I know there's a lot of steps. What I'm going to do now is I'm actually going to solve for x, because that gives me the concentration of my acid. So I'll plug in the Ka value that was provided. And then I stated that, oh, x is small, so this is going to go away. And then from here, I'm going to multiply both sides by that 0.1, just so I can cancel it out. So this is gone, this is gone. And then now I have x squared is equal to, let's see what that is. So 0.1 times 1.8 to the negative fourth. And this gives us 1.8 times 10 to the negative fifth. Take the square root, and x gives us, I believe I have it. Yeah, that's what x would give us. So now that I know that, that actually tells me the concentration of my acid. And what I can do is I can plug that into the pH formula. So that's what I'll do. I'll do the negative log of it, and then that would give us our pH of 2.38. So it is acidic, right? Because it's an acid that we're looking at, so that makes sense. And then we're going to keep going. All right, I'm going to see how far I can get with this question. So calculating the pH at different volumes. Where are we? So we're at the half equivalence point. Perfect. So we're at the half equivalence point. So this is at 20 milliliters. And this is where I said, well, if it's half equivalence point, because our equivalence point is at 40, and I just divided that by 2, which gives us 20, then I know at half equivalence point, our pKa is equal to pH. So if I figure out what my pKa is, and we have our Ka, all I have to do is plug that into this formula where pKa is equal to the negative log of Ka. So I'll plug that in, plug it into my calculator, and I didn't do it. There we go. So I'll plug it into my calculator. So negative log of 1.8, negative 4, there it is. Really? There we go. Okay, so our pKa is then going to be equal to 3.74. And then remember, well, this is telling me that pKa is equal to the same thing as my pH. So my pH is 3.74. That's done. That was easier, right? So knowing that trick is going to help you a lot. It's going to save you a lot of time. The next step, sadly, there's no way around this. We do have to do this next step. So this is going to be talking about what we're going to do before equivalence point. So that means since it's before equivalence point, we haven't added enough base to neutralize this. So this is going to be acidic. So since I know this is going to be acidic, I once again have to figure out how many moles of my acid I have, how many moles of my base, and so on. All right, so that's essentially what we're going to do right now, actually. And then we're going to use another formula that is specific for weak acid, strong base. And I believe it's also for buffers. So in case you're also struggling with buffers, I do recommend actually paying attention to this part. Okay, I recommend paying attention to all of it. But if you're really struggling with buffers, make sure to write this down. So what we're going to do is we're going to find the moles of formic acid and then the moles of KOH. Okay, so what I'm going to use is 40 mils of my formic acid. I'm going to convert that. So, and here, I kind of converted it a little bit differently, but you could have also used 1,000 milliliters per every 1 liter. That would cancel. And then now I'm going to use the molarity that was provided initially with that 0.1 for formic acid on top, the moles, and on the bottom of liters. Multiply all this out, and we would get 0.004 moles. We'll do the same exact process for moles of base. So we'll use the 39 that was provided in part C, moles of our base of KOH. We'll convert that to liters, then multiply that by the molarity that was provided, and that would give us moles of KOH. The reason why we're doing all this, and we want all of this to be in moles, is because we're going to try to use something different now. So we're not going to use an ICE table. So there's two different tables, all right? So there's an ICE table and a BCA table. An ICE table, you use that for molarity, for concentrations. For a BCA table, you use that for only moles. That's going to be like the main difference that I want you to note, okay? So ICE tables only use concentration, so molarity, moles divided by liters. For BCA, you only use everything in moles. So that's what we have now. Now that we've figured out what our moles of each are, I'm going to plug everything in. So it's similar to an ICE table, it's just the fact that it's moles instead. So now our before was however many moles we found, which was what we found here, right? That 0.004 moles of formic acid. Next, we have the moles of our OH, of our base. And by the way, I just put OH. I didn't really care about the K. That's going to dissociate or dissolve. So that's why I don't really care about it too much. So really just the OH is what we're focused on since that's the base. So now I don't care about water either. Now the next part is just to place that this is 0 because we don't know what that concentration, actually no, we don't know how many moles we have just yet because we haven't produced it yet. So then the next thing is our change. Well, what's changing? It's the thing that's definitely not changing are the moles of our formic acid because we haven't added any more volume. What we keep changing in this question is the volume of our base. So then that's why our change has to be the moles of our base. And then I'm going to subtract that on our reactant side and add it on our product side. And when I do that, when I actually do that math where I subtract these two, that gives us a really small amount. And then when I subtract these two, we no longer have any base. When I add these two, 0 plus this value, we get this amount of our conjugate base. The next thing that we have to do is we have to figure out the total volume. And now that we have the moles of our weak acid and its conjugate base, we can then find the total volume, divide it. Then that gives us our molarity or our concentration of our weak acid and our conjugate base. And essentially, what's going to help us there is that's going to help us finally determine the pH. There's a specific formula that we will use and I'll get to, but the next thing that we're going to look at is figuring out our total volume. So our total volume is the 40 mils of formic acid plus the 39 mils of our base that we just added. Add those together, that gives us 79. We would convert that to liters. Then we would divide the values that we just found. So we just found the concentration of our weak acid. We would divide that by the total volume in liters. That gives us this molarity. Do the exact same thing for our conjugate base. Divide that by our liters, our total volume, and that would give us this molarity. Now that we found those two, the next step is to find our pKa. So what's happening is to find our pKa, we'll use that same sort of formula that I mentioned before, where pKa is equal to the negative log of Ka. So we're going to find that pKa again, right? Just plugging this in, and pKa is 3.74. Next step is to use the Henderson-Hasselbalch equation, which is this. So this is the equation that you will use for buffers, that you will use for a weak acid or strong base titration. So definitely know this one and know how to use it. So that's exactly why, one, we found the pKa, so we can plug that in. That's another reason why we used our before change and after table to then get to divide by the total volume and get the molarity of our conjugate base and our weak acid. And that's what I did here. I divided that, put it in log, so log, divided those, and then add them together, and we get a pH of 5.33. So that would be our pH for when it's before equivalence point. Okay, so I'm going to probably do one more with just the equivalence point because I am running out of time, and I do want to get to the last question, which is a rate of reactions. But let me explain equivalence point and kind of the process. The process is very similar. So for equivalence point, what I would do is the same sort of concept where I would have, okay, I'd try to figure out, well, how many how many moles do I have of my acid? How many moles do I have of my base? That's what the setup would be here, right? We'd have our moles of our acid that we would solve for, the moles of our base that we would solve for, and we related that previously. And then we use the new amount, though, the 40 mils of KOH that we were given for equivalence point. Next, I would build the same sort of BCA table where I have the new moles. Remember, BCA is in moles. So I'd place all my moles in the correct values. My change must be the amount of moles of my base because that's what's changing. And I'm subtracting that. Subtract these two, and we no longer have any acid or base. We just are left with our conjugate base. Next, I would figure out how much total volume we have. So our total volume is going to be this 40 mils of acid plus the 40 mils of base, and that would give us this amount in liters. And then lastly, almost lastly, for this slide at least, we would figure out the concentration of what we're left with. So we have nothing left of our formic acid. We have just this amount left of our conjugate base. And then what I'm going to do now is I'm going to try to figure out the KB. And the reason why I'm doing this here, let's see if I can do that here. Come on. There we go. So the reason why I'm figuring out our conjugate base concentration, actually why I need the KB, is because this is our conjugate base. That means it's basic, right? So a Ka refers to something being an acid. That's what that A is referring to. If it were a Kb, it's talking about the dissociation constant for a base. So that's why I need to figure out what my Kb is in this case. So how I would do that is just using this formula where Kb is equal to Kw divided by Ka, where Kw is 1.0 times 10 to the negative 14th. And I would divide this by the Ka value that was provided, and then that would give me my Kb value. What's next is we would figure out what that Kb value is. We would build that ice table, and that would be x squared. This is really similar to what we did previously. This would be x squared divided by that 0.05 minus x. We would assume that x is small. And then from there, I would solve for x, and this is what my x value would give me, and this is my concentration of my base. What we have to do now is figure out what our POH is, and then figure out what our pH is. So this is another way you can go around this, is you could figure out what the pH is by taking the negative log of our concentration of our base. So I'd plug that in. And then now our POH is then 5.78. Let me go back. And then we would use, there it is, this formula, plug in our POH value, subtract this over to 14, and our pH is 8.22. And that would give us our value for our pH at equivalence point. Okay, so I do recommend practicing these types of questions. I'm going to do one more example of the last part that I was going to talk about, which was rates of reaction. And let me get to that. So this was Ryan's question. He asked, actually, I pretty much just put the exact question on the screen. So with this, what I was realizing that you're pretty much asked to get to is this is kind of like a beginning or an intro to figuring out the rate law. That's pretty much what you're talking about here. So it's interesting how they're how you're starting off here and not just kind of like jumping in, but that's okay. But essentially, the first part of this question, they're asking you to just look at the rates, which one's fastest, which one's slowest, and so on. So by the rates, I'm really just looking at these initial rates overall. And you're given this balanced equation, right? So you're given this reaction, and you're always going to be looking at your reactants. So before I even talk about every little thing here, I just want you to think of what we're going to focus on is how is this reaction progressing? So if we were to change the concentration of one of these reactants, would that change the rate? Would it increase? Would it double? Would it do nothing? So that's essentially what we're trying to look at and compare to see what type of, it's called a reaction order, this would be, whether it be first, second, or actually zero order. So you're eventually going to get to that, and I do have a whole playlist on that. So yay. And by the way, Ryan, I'll put that playlist, it's the rate law playlist, yeah. how to find the rate law playlist, and it also talks about the rate constant, how to find that as well. I have 3 videos that will really help you with that, but I'm still going to keep explaining this question. So with this type of question, the first part is just asking you which experiment has the fastest initial rate. And this is really just looking at what's going to be the largest number. In this case, it's a little bit kind of counterintuitive because we have negative values and you would think, oh, this is the largest number. Like, oh, no, actually, it's the smallest, right? Because it's negative. So really, because this is negative, this is the smallest. And then let me use a different color. And then that negative 1.35 is actually the largest, right? Or the fastest. So that's essentially what you're looking at here is, well, the larger the initial rate, that means the fastest it is. And the smallest, actually, the initial rate, that means it's the slowest initial rate. So that would be for part B. Now, this part C is saying, what do you think the initial rates of a reaction, or why do you think the initial rates of a reaction are different in the 3 experiments? So the reason for this is going into the idea of reaction orders, where, like I said, there's 0 order, there's first and second order. And let me talk about that a little bit here, where let's say if we had 0 order. So for 0 order, essentially what's happening is no matter how much we double, triple, or try to increase our concentration of our reactant, our initial rate is not going to change. Okay, so there's no change. So that's essentially going to be something that's known as 0 order. And essentially we're looking at how fast this reaction is going to move, or how fast, like if I were to double the concentration of our reactant, would that speed up the process to get to my product? That's essentially what we're looking at with the rate of reaction. Okay, so with 0 order, we're saying no, it won't. It won't do anything, right? If I increase the concentration of my reactant, there will be no change in my rate. But however, if I were to, let's say this is first order. If this were first order, and if I were to, let's say our reactant, I'm actually going to use NH4, if I were to double this, that means that my rate would also double. So those are going to be proportional to each other. So if you were to triple it, then it would also triple. Okay, so that's going to go hand in hand. Now, if this were, let's say, second order, this is where it changes. Let's say this is NH4 again. If I were to double this, then that means I'm quadrupling the rate. So essentially, and I don't want you to think that it's like if I were to triple it, then I would, not triple it, but multiply it by 6. Really what you're doing is you're raising it to the power of 2. Okay, you're squaring it. So that's essentially what's happening. So like if we multiplied this, then that means that's 2 squared. If I multiplied this by 3, then that's actually 3 squared, so 9. So that's what's happening with second order. The reaction is moving a lot faster. So that's what it's essentially talking about. Actually, this entire question is talking about, why do you think the initial rates of a reaction are different in the 3 experiments? Well, it's because they're at different reaction orders. So different, and actually, yeah, there's different reaction orders. Not only that, and that's actually what we're going to get into with the next part of this question, which I'll go back to the graph or the table, is this is asking you, are the initial concentrations of NH4 ammonium the same? So you're going to notice, and this also asks you here too, of NO2 minus, are they also the same? Are those concentrations the same? Well, if I were to go back to that table, then I would see, well, initially these two are. And why are they the same? That means we haven't changed our concentration whatsoever. And you're going to learn in the playlist that I have that if we keep these two consistent, then we could figure out the reaction order of our second reactant. So meaning we could figure out, is this 0 or first or second order and so on. So that's what's going to be really beneficial is you always want to have, and it makes it easier, you always want to have like these two be consistent or the same so we can end up canceling those out and then figuring out the reaction order of this reactant. So we would actually see the same exact thing for NO2 in the second experiment and the third experiment. Now these two are held constant, right? These are the same. So that means these would cancel out, and we can now figure out what the reaction order for ammonium would be because now it doubled, right? And you're going to keep seeing that. So like this doubled. And then, I don't know how well you can see that. And then this also, actually, yeah, it doubled. There it is. This also doubled, right? So that kind of ratio is going to really help you figure out, is this 0 first or second, or second order. So that's essentially the whole concept of this. I'm trying to see if there's anything else that I wanted to talk about with this. Based on your answers for that, can you determine whether or not the initial rate depends on initial NH4 plus? So for a lot of these, what you're going to do, I see. For a lot of these, what you're going to do is you're actually going to divide the rates. So it's interesting how they're teaching you this, because I would put it all in one, or at least in college, you'll learn this later, but in college they do like general chemistry 2, and they actually just give you the formula and you just plug everything in, like you would do this fraction that they're talking about, which is this, and then you would do this other second fraction for your rates, which is this, set them equal to each other and actually solve. So I won't do that here just for the sake of time, because it does take a really long time, to write it all out here. But I do have 3 examples that you can see with the playlist. So that will help you determine how, what is dependent on each other, because you're actually determining the rate law, if that makes any sense. And what this also means, by the way, zero order doesn't depend on, if our reactant, let's say, I'm just going to pretend, let's say if our reactant, which in this case it isn't, but let's say if NO2 were zero order, anything to the 0 power is 1, meaning it's gone essentially, right? 1 times something is just the other thing that we're multiplying by. So if it's at 0 order, no, it's not going to be dependent on it. So that's something that I want you to kind of understand. Okay. So Ryan says, yeah, no need to go into detail. Cool. I can watch the videos. Perfect. Yeah, the videos would definitely help you with that. And I know I have an idea where you guys are headed next, which is going to be how to figure that out. So I hope this, at least the concept, makes some more sense though. Awesome. So for everyone that either just joined or has been, watching this throughout the whole entire time, if you still have more questions, whether it be on this topic or it be on other topics that maybe I, didn't see your question for Twitter or asked it a little bit too late, or you have more questions now, what I highly recommend you guys do is tweet me your question. So tweet me your question at Hello Melissa M. That's my Twitter account. And then make sure to use the hashtag of Ask Melissa Maribel. It just guarantees that I see it and I know that you're actually asking for the live, tutoring. So our live show. So I make sure to do that throughout the week. Now, what I really recommend, because I actually make my lessons on Saturday morning. So I recommend you you tweet me your question, take a picture of it, or actually the topic of it, write it out. Make sure to do that before Saturday. So Friday night at the latest, because that's when I decide what I'm picking, is Saturday morning. So make sure to do that, not the day of, because I really planned out and, have my lesson already done. So make sure to do that. Another thing that I highly recommend, guys, is everything that all the different graphs or tables that I mentioned are going to be in the description box. There's going to be so many resources in the description box. And by the way, there's always a lot of resources in the description box for every video. So make sure to look at that. You can download the free chemistry survival guide that has all of those helpful formulas that I recommend that you understand how to use, and just makes your life a lot easier to have them all in one place. And then at the bottom, what you will find is there's more resources for, let's say, online tutoring if you would like an online tutor. And I also recommend something that I personally used, and it really helped me all throughout college, because I didn't just take chemistry. I took a lot of math classes and physics, biology. 1 year science major, you take a lot of different science classes, and Chegg Study is actually what I used, and it personally helped me a lot. What it is, it's like a homework helper. So it it essentially explains step by step. So it has like step by step solutions. And that personally was awesome because I got to see where I was going wrong with a lot of my questions, and it cleared up a lot of my questions. So not only that, I couldn't afford a tutor. So I understand what it's like to be in school and not be able to afford all the things that you necessarily need. So it was a lot more affordable than having to even hire a tutor. So, and it did the job. So I highly recommend it. It's going to be in the link. The link is actually in the description box towards the bottom. And just a little disclaimer, if you do decide to go with Chegg Study, then I do get a small commission. And that just goes to making more videos and more things for you guys for this channel. So yeah, now make sure to tweet me your questions, and I hope you guys have an awesome week. And yeah, goodness, thank you for being here. I appreciate you guys being here. I'll see you guys in the next Sunday Live. See you guys.